Welcome back. I have a beam here. Let's first assume that the density, in other words, the mass distribution in this beam is constant. Mass is equally distributed in the beam. The total mass of the beam is m kilograms. I could calculate 3 points for that beam. I could calculate a geometrical center point that divides the beam into two different lengths. The total length of the beam is L, and now you have L over 2 on one side and on another side. That point is called centroid. That's how it's called, centroid. The centroid divides the beam in half geometrically. But I can forget about geometry and divide this beam in half in terms of its mass. You have m over 2 kilograms on one side and on another side. And this point is called the center of mass, or cm. Note that the only reason why this center of mass is in the middle of the beam is because we have constant mass distribution. As you will see later, if you don't have constant mass distribution, then this cm point will be somewhere else. Finally, this beam is subjected to distributed force due to force of gravity. So as you can see, I take the force of gravity that acts on this beam and I divide it by the beam's length, and I have newtons over meter here. It's like any other force distribution that we have seen before. If you calculate the center of pressure due to this force of gravity distribution, then this total gravity force that the beam experiences, it acts through that center of pressure, and for the rigid beam, it makes no difference whether you represent it as a force distribution function over the entire beam per unit length, or as a point force that acts through that center of pressure. And that center of pressure due to gravity is called the center of gravity, or simply CG. So CG is the same like the center of pressure of the gravity force distribution. But now, what I want to do, I want to obtain the same result for the center of mass and the center of gravity, but using official mathematics. Let's say that you have the same beam, but in 3D. It has the length L, width A, and height B. It also has constant density. Let's denote the density with ρ, and its units are in kilograms over meter cubed. So if I take an infinitesimal unit volume, dV, which I can also draw here, and so I could say that this side is dx, this side dy, and this side dz, then the differential volume dV, it would be dx times dy times dz. And so density essentially tells you your mass per one infinitesimal unit volume. It tells you your mass distribution inside your beam. Each differential volume can have a different mass inside the beam. Then you have varying density. But in our case, we have constant density. It means that all differential volumes inside this beam have the same mass. And so what I can do, I can take my density in kilograms over cube meters, and I can multiply it by A, which is in meters, it's my width, and I can multiply it by B, which is also in meters, that's my height. So the meters here, they get cancelled, and so I will have a different kind of density. Let's call it ρ sub AB, and this is kilograms over meter. That way I will get the beam's mass distribution per unit length. I can do it because my density is constant along the A and B dimensions. In fact, if I look at the beam from the side, and then this would be my positive x direction, and this is my length L, then in our case, the density is also constant in the positive x direction along the length of the beam. That's why if I graph my density per unit length as a function of x, my rho AB is simply a horizontal line. And from now on, let's call it rho sub L, so density per unit length. Note that unlike force distribution, W, which you can see here, rho L does not have a direction. Force distribution has a direction because force is a vector, but rho L does not have direction because mass itself is a scalar quantity. And here you have nothing but mass per unit length. So I will simply have lines for my rho L without arrows. And now if I integrate my rho L, which is as a function of x, if I integrate it from x equals 0 till x equals L, then first of all, I will have a differential section here. Its width is dx, this here is rho L, and so I will have dm equals rho L times dx, and this dm is your differential mass, which is this differential area here. So in this context, the area under the curve is mass. And it makes sense in terms of units. Rho L is kilograms over meter times dx, which is in meters. And so you cancel out the meters and you will have dm, which is in kilograms. And so when you take your differential mass and you integrate it, then you will sum up continuously all the differential masses as you go from 0 till L. So this expression can be written down like this. The integral from x equals 0 till x equals L, and then you have rho L times dx. Now in this case, rho L is constant. You have a horizontal line. So you take it out of the integral. Here you have dx. And now you evaluate this integral. And so you will have rho L times the length of the beam, which is your mass. So remember, here you have kilograms over meter. You multiply it by meters. You cancel the meters. And you have kilograms for your mass. So m is the total mass of the beam in kilograms. Essentially, since integration is summing up all the infinitesimal masses, dm's, along the entire length of the beam, then it's logical that in the end you get the mass of the beam. But then I can also multiply each dm by its distance from the start of the beam. So here again, this is my dm, the differential area of this section, and this is the distance of dm from the beginning of the beam. And so I will have here x times dm or x times rho sub L times dx. And so as I integrate through the beam, I sum up all these differential products with an integral. So I will have rho L integral. I go from 0 till L, and then x times dx, and then I have this result, and so this is my final result, and I'm just going to denote it with mm, and the units will be kilograms times meters. Now note that this is not a moment. It has no direction. X times dm, it's simply a product of x and dm, and this mm, it's simply the summation of all these differential products. So instead of Newton times meters, you have kilograms times meters. But this time it has no direction. You simply take one dm, you multiply it by its x, then you take another dm, you multiply that by its x, and you sum up all the products as you go through the beam. However, just like we had the resultant force times some kind of special location equals a moment, and then your x bar was the moment over the resultant force, where this Fr was the resultant force due to some kind of force distribution, and m was the total moment due to that force distribution about some kind of point, and then with that you calculated your x bar, which was the location through which your Fr would act, making the system equivalent. And so just like we did it with forces and moments, the same thing can be done for masses and this quantity mm that you got by summing up all the products of differential masses and their respective distances. So you have mass times and then x bar sub cm, and that's your mm. And now x bar cm, it equals mm over the mass. So this was your mm, this was your mass. You can cancel out the rho l's, then 1l from here, and the power of 2, and you will get L over 2. And that L over 2 is your center of mass. As you can see, it's equal to your centroid, which is the geometrical center of the beam. In fact, you can calculate the centroid in a similar way. You can have length distribution per unit length, so L over L, which is essentially 1, and this dimension here is x in meters, and of course here L over L is dimensionless. It means that you have a horizontal line at 1. You can define a differential length element here. This is dx, this is 1, so the differential area here is dx, which is 1 times dx. So this differential area is your differential length element. You can integrate the function from 0 till L, then you will get the length of the beam. So L equals an integral of 1 times dx. You integrate it from 0 to L, then you evaluate it, and you get your L. That's your length. And then you can define a new function, x times dx. So you take your differential length, dx, and you multiply it by the distance x from the beginning of the beam. And then you integrate that function over the entire length of the beam. So you take this one, dx times x, and then you apply integration to it. So you will have 1/2, and then you evaluate this x squared from 0 till L. You will have L squared over 2, and let's just call this result ml. Again, this is not a moment, it doesn't have a direction, it's just the differential length times the distance of that differential length from the beginning of the beam, and then you add them all up using the integral. And then, just like with the center of mass, you have L times x bar c equals ml, x bar c equals ml over L, so you have L squared over 2 divided by L. You can get rid of this L and this power, and you will have L over 2, which would be your centroid. But as you can see, the centroid had nothing to do with density. Have you seen density in these equations here? No density whatsoever. It did not appear anywhere in the equations. The centroid doesn't depend on the density of the object. It's a geometrical center point. Welcome back. Let's now calculate the center of gravity for this beam. Again, this is the side view of the beam. Now you have your distributed load that acts on the beam due to force of gravity, and like I said before, the center of gravity is the center of pressure of the gravity force distribution. And so we would find it exactly in the same way like we found it for other force distributions. But first, remember that the force of gravity, Fg, its mass times g, the gravitational acceleration. The force of gravity is in newtons, of course, but that means that this force distribution per unit length, Wg, in newtons over meter, its mass distribution per unit length, kilograms over meter, times g, which is in meters over seconds squared. You can check the units. If you multiply them together, you will have kilograms times meters over seconds squared over meters. And so it's newtons over meter. This is newtons and this is meter. And it also makes sense that if, for example, I divide my Fg by L and M by L, well, M by L, that's my mass distribution per unit length. And if you multiply it by G, then you will have a force per unit length, which in this case is the gravity force per unit length. And this axis, of course, is x in meters. And now the total force of gravity, you get it by integrating through this force distribution. Remember, this beam has a differential element, and in this case, it has a differential force of gravity, dFg. So here as well, I have a differential element. This is my dx, then this height is wg, and now dFg equals wg times dx, or rho L times g times dx. So my differential gravity force, that's the differential area here. And so to calculate the total force, I have to add up all the differential forces. In other words, I integrate from 0 till L, and then I have here wg times dx. Then I write it in this form. Both rho L and g, they are constants, so I can take them out of the integral. I integrate from 0 till L, and then I have dx here, and so I have this result, which will give me this result in newtons. And then you calculate the moment due to this distribution about this point at the beginning of the beam. For that, you need a moment arm, which is the distance between the beginning of the beam and the differential force element. And so here as well, this would be the moment arm. And so this gravity moment about x equals 0 meters, it would be this integral, or you can write it in this form, or in this form, or in this form, and this will be your final result, which is in Newton meters. And now, Fg times x bar Cg, that's your mg at x equals 0 meters. So you calculate the center of gravity like this, which is essentially this expression here. You can cancel out a bunch of stuff here, all these things, and so your x bar Cg, it's L over 2 meters. That's your center of gravity. As you can see, all of them, your centroid, your center of mass, and your center of gravity are the same. But now I have an exercise for you. Consider the same beam with the same length. But now the mass distribution inside the beam is not the same. It's the same in terms of width and height, but not in terms of its length. Now your mass per unit length varies with length, and it varies according to this equation. m0 times 1 plus x over L, and so that's your mass per unit length. You can see that it increases with x. Now m0 is simply a constant. You can replace it with any number. And so, since rho L varies, it really means that your density, which is rho in kilograms over cube meters, it's constant at any given cross-section. So again, it does not change with A nor with B, but it does change with L. Another cross-section has another density. And so, your task now is to find the beam's centroid, center of mass, and center of gravity. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the beam's centroid, center of mass, and center of gravity. Now the centroid is found exactly in the same way like before. There is no difference whatsoever. X bar C equals L over 2 meters. It has nothing to do with this rho L. And it makes sense. Centroid is a geometrical center. Why would it have anything to do with a density or density per unit length? However, things are different when it comes to cm and cg. Now, rho L varies with length. It varies with x. Thus, to get the total mass of the beam, we integrate this beam from 0 till L. In order to have a function line for rho L, we can also write it out like this. m0 plus m0 over L times x. So you have L here you have 0, and this is the straight line function for rho L. This section here, that's your offset, and this one here, that's the slope of this line. And so you have a differential area here. Here you have dx, this is your rho L, and then this differential area, that's your differential mass. And so the total mass equals the integral of dm, or the integral from 0 till L. Now you have this function. Remember that this is your rho L, but it's not constant anymore. You cannot entirely take it out of the integral because you have your x here. Now your rho L increases with distance. And so you rewrite it like this. Then you evaluate these two terms like this. And then this will be the result. You make some cancellations. And you're left with this result. And that's your total mass in kilograms. That's the mass of the beam. Suppose that you have some kind of number for M0 and L. If you plug them in, then you will have a real number for the mass of the beam. And now what we will do, we will take this differential m and we will multiply it by x, so x times dm, and then we integrate it. So each differential mass will have its own x as you go through the beam with your integration sign. In other words, I will sum up all the differential products with integration. So I can rewrite it like this. The integral from 0 to L, x times rho L times dx. But you already know what your rho L is. So in the end, you have to integrate all this. You can rewrite it like this. Then you evaluate these terms like this. And then this is your result. You make some cancellations. And in the end, you're left with 5 times m0 times L squared over 6. That's in kilograms times meters. And let's call this summation of all the differential products mm. And now you take your mass, and if you multiply it by the distance for your center of mass, then you get this mm. Now you know the mass and you know mm. So your unknown is your center of mass. So your x bar cm equals mm over the mass. This is your mm divided by the mass. You can cancel out a bunch of stuff. Also this 2, and then this 6 becomes 3. And so in the end, you will have 5 over 9 times L, and that will be in meters, or approximately 0.555 times L meters. And there you go. This is your center of mass. So if I have this beam, then this is my centroid, and this one here, 5 over 9 times L meters away from the beginning of the beam, that's where your center of mass is. As you can see, it's different from centroid, because the density varies with the beam's length. X bar cm is more shifted to the right because you have higher mass concentration there. So as you can see, the concept of centroid and center of mass are in fact two different concepts. The centroid divides the beam in half in terms of its length, and then the center of mass is the point where you could concentrate all the beam's mass, and if you were to apply a force to this point, then the beam will accelerate in the direction of that force, but it will not rotate. The centroid doesn't care about the mass distribution inside the beam. It's a geometrical center, but the center of mass does care about the density inside the beam. X bar c equals X bar cm only when the density inside the beam is constant. Mathematically, we could write it down like this: d rho L over dx. It has to be 0, meaning that the derivative of the density per unit length with respect to x must be 0. So the change of rho L with respect to x must be 0. Then your rho L is constant. And then this holds. If this derivative is not 0, then rho L is not constant, and then x bar c and x bar cm are different. And finally, let's get the center of gravity. Since rho L equals this function, and then the gravity force distribution per unit length, it's rho L times g, then essentially you have this equation here, or in other words, this equation here. That's your Wg. We can also graph it here. It looks like this. Now it has arrows because it has a direction. It's a force distribution per unit length. You can see that since rho L varies with x, also your Wg varies with x. It makes sense because all you're doing is multiplying your rho L by your gravity acceleration, which you know is 9.81 meters per second squared. And now this offset here, it's this one here, gm0. And then this one here, that's the slope of this line. And now you find the center of pressure of this force distribution, which is your center of gravity. So the total force of gravity is the integral from 0 till L, Wg times dx. You can rewrite this integral like this, or like this. So you evaluate it like this, and then this is your result. Again, you can make some cancellations. And so in the end, this is your final result. If you remember then, the mass of the beam was 3 over 2 times m0 times L, and now the only addition is this g here. That's because Fg equals m times g. Everything else, 3 over 2, m0, and L, they're the same like in here. And now, let's calculate the moment due to this distribution about the point at the beginning of this beam. And so if you had your differential area here, you had dx here, Wg is the height, and then dFg equals Wg times dx. That's the differential area here. And now this differential area has a moment arm, which means that the differential moment due to this differential gravity force about the point when x equals 0 meters, it's x times dfg. And to find the total moment about this point, x equals 0 meters, you have to integrate this product. And so the gravity moment about the point where x equals 0 meters, we can have this integral from 0 till L, x times, and now instead of dfg, I write this one here, so wg times dx. I already know the expression for wg, and so I will end up with this integral here. Then I will have this expression after evaluating it. Then I can make some cancellations here, and in the end I will have this result. Again, remember when we dealt with masses, then we had mm, which was kilograms times meters, and it was this result. And now the only difference is that we have this g here. That's the only difference. And now you have force of gravity times the center of gravity, and that gives you this moment about the point at x equals 0 meters. Your center of gravity is calculated like this, and you're going to be left with 5/9 times L meters. You will get that if you take this guy and you divide it by this guy here. And now, this is your centroid. You have L/2 meters on one side, on another side. Then here you have your center of mass. That's its distance from the beginning of the beam. And as you can see, you have the same thing for the center of gravity. So x bar cm, it equals x bar cg. Your center of mass equals your center of gravity. And it makes sense because in the force and in this moment, you only had this additional constant here, g. And so when you divided this moment by fg, which looked like this, then your g's, they simply got cancelled out together with other constants, and you could simplify some numbers here. And so you ended up with this expression both for the center of mass and the center of gravity. This g played no role in calculating your x bar cg because it got cancelled out both in the numerator and the denominator. So x bar cm equals x bar cg. However, it does not equal x bar c. The centroid is different here. Thank you very much.